1 week break. So I just want to recap a few things. Last lecture, we saw some concepts. Like, basically, we saw what are basis vectors. Basis vectors are typically the vectors that are used to define a vector space, n, which in our case is equal to 3, linearly independent vectors used to define a vector space. And since we are going to deal with physical space most of the time, we'll stick to n equals 3. Those three vectors are mutually orthogonal or mutually perpendicular. We'll write them E1, E2, E3. They can refer to any coordinate system such as Cartesian, cylindrical, or spherical. The main concept is the three vectors are mutually perpendicular to each other. And so what that means is E1 dot E2 equals E2 dot E3 equals E3 dot E1 equal to 0, and E1 dot E1, E2 dot E2, E3 dot E3 is equal to 1. That is, their magnitude is equal to 1. So they are orthonormal vectors. So we most often won't make a mention about which three or what type of coordinate system we use. And if you go back and watch the video from the previous lecture, which I will share, I mentioned that you can define a coordinate system based on vectors that are more natural to a particular shape than arbitrarily choosing a Cartesian coordinate system or a cylindrical coordinate system. Because you might be dealing with an object that looks like a potato. It might not make sense to define a Cartesian system for that object. So for that case, E1, E2, E3 will be selected as the eigenvectors for a given shape or tensor that describes a shape. So we will see in detail how to define or derive these eigenvectors for a given matrix or a given tensor. Now we also saw what are scalars, and we didn't still formally see one thing, which is you can define a tensor. To define a tensor, you need two directions, Ei and Ej, let's say. To define a vector, you just need one direction. And to define a scalar, you don't need any directions. A scalar is you just magnitude. It has no direction. A vector has direction and magnitude, whereas a tensor has a what is called as the component. So I'll label this. This is called component. So this is just magnitude. This is magnitude, or this is called component. And this is the basis vector or unit vector. And a tensor has a component, and this Ei-Ej product is called a dyad, Dy-Ad dyad. It's not multiplication, it is not dot product, it is writing one vector next to the other to define a couple, define two directions as a combination. Now you remember or recall the example I gave about stress. The force is along a particular direction, the area is along a particular direction. These two together define the stress component. Keep remembering that example. Do you recall from 2 weeks ago, we talked about stress on a cubic element where you have a force along one direction and the area perpendicular to another direction. Those two together define the component of the tensor. Okay. A third order tensor, fourth order tensor can be written. They are defined by 3 directions, 4 directions, 5 directions, n directions. So the number of indices that appear on the components is equal to the order of the tensor. So a dyad has 2 indices, a vector has 1 index, a scalar has no index. Okay? Question? Is it okay? Are you able to recall this? We have been on a 10-day break. Okay? So you can write a scalar with just one number. You can write a vector with three numbers. Those three numbers have to obey a certain rule in order to qualify as being components of that vector. And a dyad, or sorry, a tensor has 9 numbers, and any 9 numbers cannot form a tensor. We are going to see specific rules they should follow in order to be the component of a tensor. Now let me ask you, what is the rule for scalar? That is, when you talk about a mass, for example, what rule should that number obey? If you are observing a certain mass in a frame of reference which is at rest, or which is moving, or which is accelerating, a scalar is invariant. At least in classical mechanics, don't think relativity or anything like that. Whether you are moving or whether you are stationary, as long as your speed is much less than speed of light or not, you are near in that relativistic regime, mass is constant or mass is invariant. This number which you call as a scalar should be independent of any frame of reference. How do you define a vector? That is, suppose you have, for example, let's say you have a Cartesian coordinate system, x and y. You have a point which has coordinates x0 and y0. And then you can also define a polar coordinate system, where you have a distance r and an angle theta. It's the same point denoted using two types of coordinates, x0, y0, and r and theta. If both these are equivalent representations of the same vector, what rule should they obey? You know this. I'm not asking something which you have never encountered before. Whether you measure this point in a Cartesian system, you can take a particular distance. You can call this your origin. What is this distance? x0 squared plus y0 squared square root. That distance should be the same in both coordinate systems. That is the rule. That is, in order for three numbers to qualify as being the components of a vector, what is the constraint? Their magnitudes must be invariant from coordinate system to coordinate system. Is that agreeable to you? Not clear? Tell me what's not clear. Okay, I'll give you an example. Suppose this is that origin, okay, the corner of this room. I'm standing here and I have tape measure. I have only tape measure. I can measure, or actually I'm standing here. This block is 4 squares from this wall and maybe 12 squares from that wall. So my coordinate is 12, 4. Okay. You have tape measure and also you can measure angle. So you go there and from that point to here, you just measure the length. You don't bother counting squares, just measure the length. You can also read out the angle. Let's say the length is like 14 feet and angle is 15 degrees. If both of us are representing the same vector, this 14 feet should be equal to 12 squared plus 4 squared. That is what I'm saying, that if my coordinates are correct, when I transform from Cartesian system to a polar system, the distance should remain the same. Distance is a scalar. Remember, scalar always remains the same. You have reduced the coordinates into a distance and saying if x and y, x0 and y0 satisfy this relation, then they are qualified to be components of a vector. Same logic applies. I told you Tij is not just one number, it's a set of 9 numbers. Those are the components. And for them to obey or be the components of a tensor, they have to follow some rules, and we will see what that rule is. We'll write down mathematical relationships between components of a tensor in one coordinate system and any other coordinate system. When you go from one system to another, they should follow certain rules. That is, in other words, a tensor is defined by components following certain rules of transformation between coordinate systems. That is, a tensor is a way of representing quantities that is independent of the coordinate system that you use. You can write down the physical laws of nature in a form that is now universal. You can apply it in a particular coordinate system. I can apply it in a different coordinate system, but the form of the laws will remain the same when expressed in tensor form. Okay. So this is just like a recap of what we have done so far. We also saw what is the summation convention. When two indices repeat, summation is implied. And since we are only dealing with basis vectors that are 3 in number, like 3-dimensional space, that summation 1 to 3 is just implied. So VI is actually shorthand for V1 E1, V2 E2 plus V3 E3. So if I write, for example, AI XI, what is this? This is, you tell me. A1X1 plus A2X2 plus A3X3. Okay, I is just a label. You don't like I? Sure. We'll write this as AM XM or AP XP or AS XS. You can have any, that's why this index I M P S, this is called a dummy index. There is no significance to using any particular letter. What matters is that the summation is implied. Okay, is it clear? That is, you can write AMXM or APXP. It all represents the same thing. Okay. Are you okay? I'm recording this, and tonight I plan to upload the first 2 lectures also along with today's link. Okay. So we are going to try expressing or doing some simple algebra, okay? Some simple tensor algebra, starting with, you all know about vectors, right? So what is A dot B? Dot product, right? Sorry? Yeah. So if you take a vector, any vector, you can write this as AI EI. What is this a statement of? It's just saying component along direction 1, I'm sorry, unit vector 1 multiplied by component A1 plus E2 A2 plus E3 A2. Okay. So you look at this definition of what are unit vectors, we can write E1 dot E2, which is equal to 0. So I can just reduce this. E1 dot E2 is 0 and E1 dot E1 is 1. This relation is expressed in a more compact form, like almost like saying EI dot EJ is equal to 0 if I is not equal to j and is equal to 1 if I equal to j. Right? This type of this function, the way it is defined as 0 if the 2 indices are not equal and 1 if the 2 indices are equal, this is given a name. This is called delta ij, the Kronecker, forget the spelling, Kronecker delta function. So wherever delta ij appears, you can just take that this is the meaning. Okay. So if I take two vectors A and B, I can write this is AI, EI dot, and B is some other vector. It is still in the same basis, still in the same coordinate system, same basis, but I can write this, or I should write this BJ, EJ. To show that I and J are independently varied between 1 and 3. So they can, it's like saying, this is like almost like saying double summation AI, EI dot BJ, EJ, I runs from 1 to 3 and J runs from 1 to 3. This is the compact version of that. You have think? What happened? Tell me what's not clear.
Or I forgot what happens.
What happens where?
What does the hat mean again?
Oh, hat. The hat is essentially the unit vectors. So we talked about Cartesian, right? So you can say IJK, that is usually used to denote a Cartesian coordinate system, or you can say ER, E theta, and EZ, which is used to denote a cylindrical coordinate system. Without telling specifically which coordinate system we are using, we use 1, 2, 3 to show that we are in some orthogonal coordinate system. And 1, 2, 3 are three mutually perpendicular directions. They are mutually perpendicular, so they can be radial, tangential, or they can be x and y. Whatever it is, 1.2, 2.3, 3.1 is always 0 because they are perpendicular. 1.1, 2.2, 3.3 is 1 because their magnitude is unity. That is what this statement means. This applies to any orthogonal coordinates. So when we write it this way, and when we say the index for 1 and I and j are independently varied from 1 to 3, we are just checking out all possible combinations of I and j. Okay. So now, from now on, I'll stop writing that summation. So I'm going to write, this is AI, Bj. It is just two scalars. I'm allowed to multiply scalars, right? There is no restrictions on multiplying scalars. And then I have EI dot EJ. So this is AI, Bj, and we just saw EI, EJ is delta IJ. This is essentially a summary of this information. If I and j are the same thing, it is 1. If I and j are different, it is 0. Okay. If I and j are different, it is 0. So when this is 0, the whole thing becomes 0 because it's like something multiplied by 0. So the only cases of interest are when the only combinations of interest are when I equals j or j equals I. Right? When you write delta ij, only delta 1, 1, delta 2, 2, delta 3, 3 are useful. Others are all zeros. So I can write, what I'll do is A dot B is equal to set j equal to I. So whenever j appears, replace it with I, AI, BI, delta II. Delta II is just 1. this is 1. So this is nothing but AI, BI, or A1, B1, plus A2, B2, plus A3, B3, which is a result you know all along. You always knew this. This is just dot product of two vectors. If A1, A2, A3, B1, B2, B3 are the components, you know this from the beginning. All we have done is do it in tensorial form or like in indicial form. Okay. So we have a tensor A. The book uses how it represents a tensor is it uses A, it writes A in bold font. Obviously, when I write on the whiteboard, I can't do bold. I can't give you that visual effect. I'm going to use the symbol, or I'm going to put two dashes above a quantity to denote tensor. Second order tensor most commonly, sometimes third order, fourth order. For vector, we do this. For scalar, we just write this. Okay, this is the convention. So if you take A, this is Aij, Ei, Ej. Your question? So can you expand this m times b? Scalar multiplied by a vector. So this is m multiplied by vi, ei. So this is mvi, ei. I mean, it's like stating the obvious. You know what mvi, vi is? It's momentum vector, velocity multiplied by mass, scalar multiplication. Take this quantity, A, multiplied by a scalar. That would be m multiplied by aij, ei, ej. To remind you, we call this unit vector or basis vector. We call this, what do we call this? Dyad. It's called a dyad, di standing for two vectors that are combined. When I say combined, it is not added, it is not multiplied, it is not dot product, but combined. They are combined to denote that they are a pair. That's why they are called a dyad or three vectors, triad, quadrad, and so on. So when you do this, you get m aij multiplied by ei ej. What is this quantity? It's almost like saying the scalar is multiplied with every component of the tensor, just like the scalar is multiplied with all the components of the vector. Okay? P dot B. This is BIEI dot BJEJ, which you just did, just you have to put A equals B or B equals A. This is VI squared. This is BIVJ delta IJ. This is VI squared, or if you want to write it as VI, this is equal to V1 squared plus V2 squared plus V3 squared. I'm painfully stating the obvious things that you already know to help you connect it with the things that you don't know right now, and we can kind of bridge forward. Okay? Okay so far, right? So far what we have done is scalar multiplication, this here is scalar multiplication. This usually we call dot or inner product. Dot or inner product. Okay. So now consider this quantity A dot B. The tensor A dot product or inner product with a vector. I'm just first going through how you would do the algebra. There is no physics in any of this. We are just trying to learn the rules of the game. Okay, there is no, we have not yet done any deformation, force analysis, kinematics, nothing. We are just equipping ourselves with the tools. How will you write this? A, wherever it appears, Aij, Ei, Ej. Dot V will write Vk, Ek. Why did I choose a third index than Inj? Because we want to count, or so it's like saying there are two directions involved with the tensor, one direction involved with the vector. We want to account for all possible combinations. So we have to make sure that this index is separate to begin with, and then we'll see how the algebra takes. Are you okay? So once you write it this way, you have essentially written this tensor and this vector in terms of their components. What are components? Are they scalars or they themselves are vectors? The components of a vector is like three numbers, three scalars. The components of a tensor is 9 numbers or 9 scalars. So you can take this number Aij and multiply it with Bk, and then you have Ei, Ej, which is a dyad, dot Ek. When you do this operation, keep the sequence the same. Don't put Ek ahead of the I. If it appears as I, J, K in that order, preserve the order. Okay. So you have Aij, Bk, Ei. I told you Ei and Ej, they are combined. They are not themselves a product, sum, or a dot product. Okay. So you can leave the Ei there, but you have Ej dot Ek, which I'll write delta Jk. I have two unit vectors J, Ej, Ek. If I do a dot product of them, I'm writing that is delta Jk. Take a minute, tell me if this makes sense to you. If it doesn't, please say, we can discuss. Yes.
I mean, why to write in the same order? So I, J, K. Can't we write J, I, and K?
So when you previously did vector dot products, you do A dot B, you end up with a scalar, which is the same scalar you will end up with if you do B dot A. The mathematical term for this is commutative, meaning the order is not important. But when it comes to operations involving a tensor is always defined by at least two directions. We are agreeing on that. When you say two directions, it matters which direction comes first. So naturally, sequence is important here. When you define a vector based on only one direction, there is no sequence here. It's only one. You can do it. You can only do it one way. That is why when we have tensor operations, it matters to preserve that sequence because EIEJ is different from EJEA. So just we want to keep it in the same way they appear and start executing these operations. So if you have this EI, EJ, dot EK, EI. This is an operation in between. You'll get delta JK, and then you have EI, EL, EL, and this is now a scalar. You can write a scalar in front also or behind. So you can write this is delta JK, EI, EL, which is now the new diode. So this is the first diode 1, diode 2, and then you end up with a new diode. Okay, so that is why order matters because the quantities that you end up with A dot B will be different from B dot A. We'll do that also. So are we good here? Please, I ask you if you can think about it and tell me. Is it Chris?
Or,
Mark, you okay?
I think so.
Okay. When we do the other operation, if you can do it yourself, you'll feel better. When we do the V dot A. Okay, we'll try it. So I have delta JK. The next step is always, if you see a delta function, you can set K equals J or J equals K. That's basically going to reduce. Wherever K appears, replace it with a J. So this is AIJ, VJ, EI. Look at this quantity. There is a vector, there is a basis vector EI, and then there is this quantity. How many free indices does this quantity have? I saw you saying 1. Which is the one? I is the only free index because you have already said VJ repeats twice, so you have to sum over J. So this is shorthand for AI 1 V1 plus AI 2 V2 plus AI 3 V3 EI. So you see whatever it is, this may be a sum, but this is still a scalar multiplied by a unit vector. What is that quantity? A scalar multiplied by a unit vector, a component multiplied by a unit vector. That's a vector, right? This is a scalar or this is a component that depends on I. And this is the basis vector. That would make this whole quantity a vector. So we started with a second order tensor. We dotted it with a first order tensor, otherwise known as vector, and we ended up with a vector. So the order 2, order 1 resulted in a quantity whose order is 1. Okay. Is this something you have seen before? Am I harping too much on something you already know very well? Yes, no, it's perfectly okay to say no because I'll feel much better that I spend time than you say, oh, I know all this. Why did you waste time? So am I good in talking about this? Good? Okay.
Right.
All right. So now I want you to do the opposite operation. P dot A. Can you compute that quantity? That is BI EI dot A JK EJ, EK. And at the end, you are going to answer me, is A dot B same as B dot A? You're going to answer that. So this is BI, A, J, K. Preserve the order. Preserve the order of appearance of the indices on the unit vector. I don't care about the scalars, but on the unit vectors, you have to preserve the order. So this is VI AJK, EI dot EJ times EK. Or this is VI AJK delta IJ EK. Thank you. Delta IJ EK. So this is, I have delta IJ. So I'm going to set J equal to I. Wherever J appears, replace it with I. This is VI AIK EK. Delta II is 1. So I'm taking the liberty of skipping one step. And slowly I'll take liberty of skipping more steps. So this quantity VI AIK and this quantity AIJ VJ, are they the same thing? Is it the same quantity you end up with whether you do A dot B and B dot A? This is a serious examination question. Like I give you like two quantities which do some operation like this and ask you to check whether are they the same thing. How will you check this? We'll see a more technical way of checking this, but for now, the easiest way to check is write out the expansion and see if you end up with the same quantity identical on both sides. Okay, so let's expand this. You have to sum over I. So this is V1 A1K plus V2 A2K plus V3 A3K multiplied by EK. This is V1, just for convenience, I'll rewrite the other one also next to this so that you can do the comparison easily. So this is V dot A, this is A dot V, this is V1 A I1 plus V2 A I2 plus V3 A I3 here. And if it makes your comparison simpler, instead of using I, can I use K? Is it okay? It's just a dummy index, right? It's like your name. Instead of your name, shall I use your name? So clearly they are not the same expression. You are getting A1K, whereas here you are getting AK1. So you're not ending up with the same vector with both the operations. So it's safe to say B dot A is not equal to A dot B unless A is symmetric. Now we have to see what is symmetric. Okay, question?
Yeah.
Yes.
So, I think I missed this part. Why there we keep the EI and we make the delta JK, but here
Yeah.
we.
So if you see here, this is EIEJ. Like I always said, the tensor is always about a combination of directions. And when you do the combination or combining, the sequence matters, whether it's 1, 2 or 2, 1. That is EIEJ, which is different from EJEI. So if you take EIEJ and then dot that with a vector EK, you will have to always do the operation from, how do I say this? Not necessarily left hand side, but if it is J and K with the dot product, that operation is neatly defined. Suppose if it were like this, I and J, you would do that first, and then before you do any operation on K. That is why here you have delta JK, whereas here you have delta IJ. So if you do the comparison, here you end up with 1K, here you end up with the transpose of that K1. So these two cannot be equal generally unless K is a symmetric matrix or a symmetric tensor. Okay. So that brings us to a couple of definitions. Number one, what is a symmetric tensor? It is the tensor for which AJI is same as AIJ, or the tensor or the transpose of the tensor is equal to the tensor itself. So for that tensor, you write A11, 22, 33, and then you have 12, 13, 21, 23, 31, 32, 33. So these two quantities, this quantity and this quantity, and these two quantities are equal. That would be a symmetric tensor. We also have an anti-symmetric tensor for which A transpose is equal to the negative of A and AJI is the negative of AIJ. So for that tensor, you have A12, A13 minus A12, A23 minus A13 minus A23. What about the diagonal elements? If you do this, if you apply this for AII is equal to minus AII, what does that mean? What is 0? Oh, you said something. What is 0? It means AII must be 0. That's the only way that a number it's the negative of itself, which means all the diagonal elements are zeros for an antisymmetric tensor. That's the only possibility for this to be true, right? Number 3, unit tensor. So it's given a symbol I. Its components are defined as delta Ij, Ei, Eg, which is 1, 1, 1, and everything else is 0. The unit tensor has the obvious property that if you take a tensor and do a, sorry, if you take any quantity, let's say for example a scalar dot I will give you m m m, or if you take a vector dot I, what will you get here? How will you evaluate this? Following the rules that we have done so far. This is Vi Ei dot, can I write I as delta Jk Ej Ek? Would that throw you off terribly? Instead of course I use Ij here and using Jk here, is that a problem? No, right? You understand that it's just a name, right? So then I have Vi delta Jk, and then I have Ei dot Ej multiplied by Ek. So this is Vi delta Jk delta Ij Ek. So wherever J appears, I'm going to set it equal to I. That's what delta Ij means. Good. So this is Vi delta Ik Ek. I have delta Ik. Wherever K appears, I'm going to replace it with I. This is Vi Ei. And what is Vi Ei? That's just the vector V. So the dot product of vector and identity or unit tensor gives you the same vector. Dot product of scalar and the unit tensor, scalar product of a product of a scalar and a unit tensor gives you just the scale value m times I. Can you try A dot I? Can you try? That would be Aij Ei Ej dot delta Kl Ek El. So Aij delta Kl Ei, I have Ej dot Ek multiplied by El. What is Ej dot Ek? Delta J. So this is Aij delta Kl multiplied by delta Jk Ei El. What is Ei El? Okay, you are very responsive, thank you. But we should also allow others to give responses. Good, but like tune it down a little. So you can plan it something like, I will answer the every third question, not every question. Others, please, what is Ei here or what is Ei next to EL? Dyad. It's not delta, there is no dot here. It's a dyad, it's a combination which is not a sum, not a product, not a dot product. It's a combination. That's what I've been saying. What is a dyad? It's just like a tag 1, 2, denoting two directions in a particular sequence. You're okay? Tell me.
So I thought it's delta. Not delta.
No, this is not delta. So there is Ei. So initially it was Ei dot EK. The dot is between J and K. So you do a delta Jk for that. Ei is still whatever Ei is, it's still there. El is still there. So now they just come next to each other and form a dyad. So First, let's resolve this delta. Wherever k appears, replace it with j. Aij delta jl ei el. I have delta jl. Wherever L appears, I'm going to replace it with J or the other way. So this is Aij, Ei, Ej. What is Aij, Ei, Ej? It's the tensor A itself. It's the tensor A itself. Okay, so unit tensor is the quantity which when combined with any quantity or which when dotted with any quantity gives you back the same quantity. Which is what unity is. You take one and multiply with anything, you get the same number, right? It's just the extension of that to tensors. All right. So we have seen so far, you can do operations like addition. Just like you add scalars or vectors, you can also add tensors. Like for example, if you write C is A plus B, this is same as writing Cij is Aij plus Bij. The components of the sum tensor is are the sum of the components of each tensor. Pretty obvious thing to say. You can do addition, you can also do subtraction. It's really the same thing. Multiplication. So if you write C equals A multiplied by B. Over here, order is preserved. If the order is 2 or 3, it is 2 or 3 in the sum also. In this case, this is same as writing. We don't know about C yet, so we'll just deal with A. A and B are two independent tensors, so we'll write this as Aij, Ei, Ej multiplied by BKL, EK, EL. So this is Aij, BKL, EI, EJ, EK, EL. What is the order of this quantity? How many independent indices are in this quantity? Four. 1, 2, 3, 4. You need, it's like saying I have a quantity that depends on two directions. I'm combining with another quantity that depends on two independent directions. So the total combinations is 2 times 2, 4. So it depends on the sequence of 4 directions. How many components does this tensor have? So if I write this is equal toCijkl EI, sorry. So this is like writingCijkl equal to Aij BKL. How many components does this tensor have if you write it in matrix form? You have three, sorry, if you have two, if it's a second order tensor, how many components? T squared. 9, right? So if it's a first order tensor, that is 3 power 1 components. It's a second order tensor, that is 3 squared equal to 9 components. If it's a fourth order tensor, that would make it 3 to the fourth, 81 components. Basically, it's a matrix of 9 by 9. Actually, that's a misstatement because I know I can visualize 2D space with a matrix, but I don't know how to represent 3D, 4D, and 5D. Okay, it's just not easy. We'll just leave it at 91 components or 81 components. Sorry. Okay. This is multiplication, which is combining two tensors independently. There is also another form of multiplication which you are more familiar with, which is inner or dot product. So if I write, I'm going to write C, okay, or I'm going to take the quantity A and dot it with B, dot it with B. At this point, I don't know what the resulting quantity will be. Will it be a second order tensor? Will it be a third order tensor? Fourth order tensor? I don't know. We'll see. So this is A Ij Ei Ej dot B KL EK EL. Now, without following through and finishing all the steps, can you tell me the order of this quantity? Are you saying 3? Okay, any other response?
OCM
4? You are saying 3 or you're changing your answer? 2. Okay, let's just do it. We have 2, 3, 4, all possible options. You have to try. Okay, so this is A Ij B KL EI EJ dot EK, which is delta JK EL. Me. Okay. So then I have Aij. Wherever K appears, I'm going to replace it with J, B, JL, EI, EL. Now tell me what is the rank of this quantity? Well, how many free indices are there? 2, which are I and L. J is not a free index. I hope you saw that. You will sum over J and you'll be left with I and L, which means this has 9 components, that is 3 squared, which makes this a second order tensor. So you can write, if you write C is equal to A dot B, that is like writing Cij equals Aij times Bjl. Sorry, CIL is AIJ times BJL. J is summed over. So we saw multiplication variant 1, which is just dyadic multiplication without doing any operations. This is inner product. We'll call it variant 2. Okay. Are we clear? You saw two variants which are different from each other. We'll see a third variant. We want to consider the quantity A. I'll put a colon to denote what is called as a double dot product, or sometimes also known as contraction operation. Double dot product. Okay. Now what is this double dot product? We'll write this equal to Aij B KL EIEJ dot EKEL. All I've done is put a colon here. We haven't talked about the colon. So the colon represents dot product between the inner and outer pairs in any order. If you really think about it, all I've given you is like rules, tricks. There is no heavy concept in here so far. It's all tricks, little things to remember. So this is like writing A I J P K L delta Ij times delta IL, sorry, delta JK times delta IL. Wherever K appears, replace it with J. Wherever L appears, replace it with I. So this is Aij multiplied by Bji. What is the rank of this quantity? How do you determine rank? Count the number of free indices. How many free indices? Did you say two? Two?
IG.
But you also have the summation convention. What about it? You want to say something? So over here, J is summed over. Only I and L are free indices, meaning if you do the summation over I and L, you are not going to reduce it any further. You're just going to write the tensor. Over here, J is not a free index. You would have done the summation. I is also not a free index. So this has 0 free indices, which makes this quantity a scalar. Are you seeing this? So this quantity has no pre-indices, or in other words, its order or rank is 0, which means it's just a sum of several numbers. In the end, it's a scalar. So this quantity A double dot B is, we can write it C, which is only a scalar. Over here, the C is a second order tensor. Over here, the C is a fourth order tensor. So we have seen three variants of multiplication here. One that results, you can combine two tensors to get a fourth order tensor. You can combine the two tensors to get a second order tensor, which is like instead of 4, you are getting only 2. You can combine the same two tensors to get a zeroth order tensor or a scalar. Three ways of combining. So in the book, all these are discussed, but not in the sequence that I am doing this. Okay. Sometimes the book goes into, I will frequently skip some topics from the book. Now I feel like some of them are a bit too dense and advanced. Sometimes I will skip them for clarity. Okay. Or sometimes do them out of sequence. All right. Yes. Now, whatever I say in class, corresponding sections are the ones that will be covered for the exam. If I give you specifically like a reading assignment saying read section 5.3 by yourself, that means 5.3 you have to read it fully. But right now we are going through chapter 2. I am doing some sections. Maybe at the end of this discussion, we can make a list of section numbers that you should kind of go. But tonight, when you go back, you can go and find all this in the book, but you have to go through section or chapter 2. Okay. The just that since you asked about exam, the exams are, I designed them to test competence. Meaning, if you have taken this class, do you know the basics that are expected of you in this class? Not advanced application of the material, but minimum basic applications. The project component, which also has 25%, will test you for some advanced application like choosing a problem, applying the techniques learned in this class for a engineering problem, and trying to come up with a solution, maybe using FEM or finite volume method or some kind of numerical method to solve the problem and present the solution. That is more advanced. That is only 25%. 50% is for 2 exams, which is competence, and the homeworks are even like easier in the sense that they will only make you do the basics. So 75% of the course is actually that is within your grasp. Only the last 25% will push you further. Okay. Which brings me to homework also, which I need to post because now we have done enough discussion that you should be able to start attempting homework. All right, so we have talked a lot about vectors, basis functions, coordinate systems, and then different types of operations. Now we saw dot product. What is the other major thing which you have seen in vector algebra before? We should see cross product, right? We have spent a lot of time on dot. Let's talk about cross product. So you know from your previous vector algebra classes, A cross B is E1, E2, E3, A1, A2, A3, B1, B2, B3. You know this. This is cross product. How we calculate it, right? If you expand this, of course, you're going to get A2, B3 minus A3, B2, E1 minus A1, B3 minus A3, B1, E2 plus,
Even
or actually, hold on, equal to minus 1, 1 plus 1 plus minus 1 power 1 plus 2 plus minus 1 power 1 plus 3 E3 or A1 B2 minus A2 B1 E3. This is cross product or by expanding the determinant. Okay. Now, yeah.
what is the power 1 plus 1, 1 plus 2?
Okay. Let me back up a little. Okay. So generally, when you are expanding a determinant, suppose for example, you have actually, I'll come back to that. Okay. Let's not go there because it's not the right place to say this. So to evaluate this, and later we want to see what happens when you do A cross B, where both A and B are tensors. We want to see those type of combinations. First thing we want to see is, if you take a tensor A, it is represented by a matrix which is A 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. You can compute the determinant of this matrix. Now, I want to make a clarification here. When you take a vector, you can calculate its magnitude. It's well defined, A1, V1 squared plus V2 squared plus V3 squared. When you take a tensor and you get its determinant, you are also getting a scalar, but do not think this determinant is some sort of magnitude for the tensor. It is not. For a vector, magnitude is easy. It is the length of the vector measured in some way from an origin. But for a tensor, the determinant is a scalar, but not to be confused as a magnitude. Okay, so I'll maybe write it here. Determinant of A is a scalar, but not to be thought as the magnitude of the tensor. It's almost like saying a matrix is a way of representing a collection of 9 numbers, and the matrix containing the 9 components of a tensor represents the tensor, but the matrix itself is not the tensor. That making clear? There is the components of the tensor are written in matrix form, but the matrix itself is not the tensor. Why I say that is because you can take any 9 numbers and write them in a matrix form. They don't have to have a relationship with each other. But if those 9 numbers have to be the components of a tensor, they have to obey certain rules. So it's like saying a tensor is represented by a matrix, but not every matrix is a tensor. Okay. So when we want determinant of A, what we do is you can take any one element, A11, multiplied by -1. So this is 1 comma 1, the position. 1 plus 1 multiplied by the minor, which is A22, A23, A32, A33. And then you can take the second element plus A12 multiplied by -1 power 1 plus 2, A21, A23, A31, A33. Plus third element plus A13 multiplied by -1 power 1 plus 3 multiplied by A21, 22, 31, 32. This is true for any matrix. Okay. So determinant of A can be written in this form. Now, we're going to introduce something here, and not in the most natural or obvious way, and then ask you to prove or convince yourself that the notation I introduce and this way of determinant are one and the same. First, we are going to define what is called as the permutation symbol or tensor. Permutation tensor, which is defined as epsilon ijk is equal to so this is obviously a third order tensor. It has 3 indices. It's a third order tensor. It is equal to 1 if I, j, k follow or form an even permutation. Meaning, what is the even permutation? So I have I, j, k. I'll write them in a circle like this. Okay. I can take values, 1, 2, and 3. So can j and also k. We know these. If I write epsilon 1, 2, 3 or epsilon 2, 3, 1 or epsilon 3, 1, 2. That is, if I'm going in the clockwise direction. These are all called even permutations. They are called even permutations. Like, don't ask me why I'm saying you. What is your name? You can know. Can I ask you why are you? It's your name. They are called even permutations. So these are even permutations. And even permutations take the value 1. It's like saying if you go in sequence, we'll give you a tag 1. If you go in reverse sequence, like for example, if you have epsilon, I'll swap one of them, 2 and 3. Or I'll swap one of them, 1, 3, 2. Or I'll swap the third combination, which is epsilon 3, 2, 1. These are called odd permutations. That is, you can also do the same with the other epsilon 2, 1, 3 I'm sorry, yeah, we already got 2 and 3. So there not be more, so what are the distinct ones here? 2 and 3. 1, 3, 2 is already here. 3, 2, 1 is already here. There'll still be 2 permutations.
3, 1,
2, 3, 1. Epsilon 2, 3, 1 and epsilon
3, 1, 3.
3, 1, 2. 3, 1, 2. And in the third line, you're going to have 2, 3, 1 is already here. 3, 2, 1, 2, 3. 1, 2, 3 is an even permutation. 1, 3, 2, 1, 3, 1, 2. 1. So we already have the 1, 1, 1, 2, 3, 1, 3, 2. So then if you have 3, or say 2, 2, 3. You should have 1 starting with 1. 1, 2, 3, 1, 3, 2. Okay, let me not waste time on this, but think of what's the 6th permutation. These are called odd permutations. And those odd permutations are given a tag -1 if I, J, K form an odd permutation. And then if any two repeat, that is, if any two repeat, like for example, epsilon 113 or epsilon 223 or any two repeating, these are called any two or three repeating indices. These are called null permutations. And null permutations are given a tag of 0. If I, J, K form a null permutation. So just to recap, I wrote what is determinant, and then I suddenly jumped and started writing what is the permutation symbol defined in this way. This is what I've done. Now we are going to write an expression for the determinant in terms of this permutation symbol, and then prove that that expression and this are one and the same. Okay. So determinant of A is equal to epsilon ijk AIM is equal to A1I, A2J, A3K. I'm giving you this expression, and then we want to prove that these two expressions are equivalent. You may ask why? Why should we do all this? The utility is instead of dealing with this sort of a matrix, this sort of a lengthy expression, suddenly if I tell you determinant of a matrix is compactly written in terms of the permutation symbol and the the components, that makes the algebra of further operations much easier. So we are deriving this purely to make future manipulations manageable. Okay. So it's about 1 minute left. So this is one of the homework problems in the first homework. It is for you to start with this expression and through substitution prove that these two are equal. Okay. If you go to page 21 in the textbook gives you some hints which you can use as a starting point. So start with page 21 from the textbook. And we will see elements of this in the next lecture briefly, but this is one of the homework problems for you. Okay? I mean, once I post the homework tonight or tomorrow morning, you will see. So Thursday we'll have a regular meeting. Originally, I was planning to hold that makeup session on Wednesday, next Wednesday, February 12th, but some important departmental meeting fell on that date. So I'm now pushing it to 19th and 26th. Two Wednesdays, 2:30 to 3:55. Okay, 19th and 26th. Okay, so hopefully we should. And I'm planning for first exam, which is coming up the week before, the last lecture before spring break. We will mostly do this unit on tensors and kinematics. Only two units for the first exam. Okay, so we still have time to finish all that. Is that dates? Everybody okay? Are you okay? You have what, sir?
Bank appointment.
You'll miss some part of the lecture.
Not sure, because if the appointment is one, I'm not sure how long it is.
Okay. How about we do this Wednesday? Like this Wednesday and 19th. Tomorrow. It will also give me, see, if I have the extra time now, it will be more useful for me to cover the topics than have it later. It's like you can't suddenly think, you need time to think about all this before the exam. So how about tomorrow and 19th? Tomorrow 2:30 to 3:55. 19th 2:30 to 3:55. Okay, no problem. Okay, so tomorrow 2:30. All right. Thank you. I'll post these lectures tonight, okay, and share the link with you.